We've all been there, right? It's, I don't know, maybe 75 degrees out, but the air just feels thick, heavy, like you're walking through soup.
Mm-hmm. That muggy, stifling feeling.
Exactly. And that feeling isn't just about humidity. It's driven by something much more specific, a metric called the dew point.
Right. The dew point, or $2, is really the core measurement for true atmospheric moisture. And, as you said, for human comfort.
So for today's deep dive, that's our mission, understanding the dew point. In simple terms, what is it?
Simply put, it's the temperature that the air has to be cooled to at a constant pressure for the water vapor in it to hit 100% saturation.
And that's the point where it starts to condense.
That's the point. It's what causes fog, dew, and your general discomfort on a humid day.
And we usually calculate it from two things we can easily measure, just the regular air temperature and the relative humidity. Okay, so let's unpack that. Why does this one number, this one temperature, matter so much to us?
Well, because it controls how well your body can cool itself. Human comfort really drops off once the dew point gets past about 18 degrees Celsius.
That's pretty specific.
It is. And above 21 degrees, we consider it oppressive, tropical, because your body cools itself by evaporating sweat, and when the dew point is high, the air is just too saturated. It physically can't accept any more moisture.
So your natural air conditioning system just shuts down, the sweat has nowhere to go.
Exactly.
Right.
It's exhausting. But on the flip side, a dew point below 10 Celsius, that feels wonderfully dry.
Okay, so if the forecast says the dew point is over 21, I know it's going to be a sticky day, but this number is useful for more than just comfort. I was reading about its use in aviation, which is just fascinating.
Oh, it's critical for pilots. See, the dew point tells you the absolute amount of water vapor in the air. Relative humidity changes with the temperature, but the dew point is a more stable measure.
And pilots use that how?
They look at the spread, the difference between the air temperature and the dew point. That spread gives them a quick way to estimate the height of the cloud base.
So the bottom of those big, puffy cumulus clouds.
That flat bottom is literally the altitude where the air has cooled down enough to meet its own dew point. That's saturation right there in the sky.
Wow. And if it's that important in the sky, I imagine it's just as critical on the ground for, say, building engineers.
Even more so, you could argue.
Yeah.
In HVAC design, you live and die by the dew point. If any surface in a building, a cooling coil, a vent, an inside wall dips below the dew point of the surrounding air, you get condensation.
Which leads directly to water damage and
mold, a huge, expensive problem to fix.
You know, finding the most efficient solution for complex calculations, whether that's in atmospheric science or in business, it often requires some expert help.
That's very true.
And if you're looking for that kind of edge in things like AI training, automation, or software development, this deep dive is sponsored by Embersilk. They specialize in figuring out where intelligent agents can make the biggest impact for your business. You can check them out at embersilk.com.
So, getting back to the calculation, it's actually pretty challenging. The whole thing depends on finding what's called the saturation vapor pressure.
And that's what exactly?
Think of it as the air's absolute moisture ceiling at a given temperature. It's the maximum pressure water vapor can exert before it's forced to condense into liquid. And that relationship is nonlinear.
Meaning it's not a simple one-to-one increase.
Right. It compounds. As the air gets warmer, its ability to hold moisture shoots up exponentially. This makes the math tricky.
So how do we actually calculate it? What are the main formulas?
There are really two big families. The first is the Magnus type. It's computationally cheap. It gives you a direct answer without a lot of heavy lifting.
The quick and dirty version.
Sort of, but it's still pretty good. It's great for most web calculators or hobbyist use. The air is usually less than half a degree Celsius.
Okay, and the other one? For more serious work.
For high-grade meteorological use, you want the Buck equations. Buck is much more accurate across a huge range of temperatures, and it even handles the difference between saturation over water versus over ice.
Which would be critical for anything below freezing.
Absolutely. The only catch is that you can't solve it directly. You need a computer to iterate and find the answer.
So it's more complex. But here's what I found interesting, this accuracy paradox.
Yes, this is key. While the Buck equations are more accurate in a perfect world, in the real world, your sensor is almost always the biggest source of error.
So your relative humidity sensor might be off by 2 or 3%, and that little error completely swamps the tiny improvement you get from the better formula.
Precisely. The formula isn't the limiting factor, the measurement is.
And that drive to constantly refine these formulas, even when the sensors are the weak link. It really shows this, human effort to optimize everything. We're always pushing to make our environments better, more efficient.
It's inspiring, isn't it, to see that level of scientific rigor applied to something as fundamental as our own comfort. We're learning to measure and manage our world with incredible precision.
It really is. And to leave you with one final thought on that, the highest dew point ever recorded on Earth was 35 degrees Celsius. That's 95 Fahrenheit.
Wow. In Dhahran, Saudi Arabia.
Yeah. And just imagine that for a second. That means the air temperature could not fall below 95 degrees without water literally condensing out of it. It must have felt like breathing in a steam room.
It truly highlights the extremes of our atmosphere's capacity for moisture and our own ingenuity in figuring out how to live within it.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.